This meeting is being recorded.
Hello, everyone. Welcome back to the AAS YouTube channel. That was a little surprise. And this is part of the good stuff. This is the AAS Journal Author Series, and I am very happy to have Karim Shariff with us today. Oh, man, I blew that intro. Hello, Karim. How are you doing?
Fine. I actually have to get rid of my plotting program, which seemed to just come up. I think I've done it. Okay.
Technology, it always works. It's truly great. And Karim, what's your geolocation? Where are you at?
So I'm at NASA Ames Research Center,
Cool.
which is in Silicon Valley.
Mm-hmm.
So Mountain View is the address, a few miles south of Stanford University.
Mm-hmm.
And the weather is really great. It's warm. We have a beautiful campus here.
Cool. Very good. Very good. Yeah, usually, by the time you roll into September, October, I think I personally is where California gets some of its best weather.
Uh-huh.
It's actually really nice. And it is September 12th of 2024 as we record this, and I'm in Phoenix, and we are starting to cool down. It was a very pleasant 70-something this morning, so we're starting to cool down from the triple digits, although we'll still hit it a little bit later today. So
good.
All good. Let's see. And Karim, what do you like to do for research?
Well, so I'm basically a fluid mechanician. I was trained in mechanical engineering.
Yeah.
And so much of my early research was in vortex dynamics and simulation of turbulence.
Cool.
But around 2000, actually, I became interested in circumstellar disks because there was a group here at NASA Ames working on disks. But it wasn't until a few years after that I actually began to actually contribute to the field.
Very cool. Very nice. And we're going to cover one of these lovely contributions in this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Padé, a code for protoplanetary disk turbulence based on Padé differencing. And Karim, take us away.
Okay. So basically the code, the paper describes a code. We call it Padé because the scheme that it uses is Padé differencing. Now, Padé differencing has been used in the aerodynamics community, I would say, starting around 1992 when Lele made it very famous.
Okay.
But it hasn't been used in the astrophysics community. Well, because it's not really that general.
Okay.
So for example, current codes such as Athena, Fargo, etc.
Yes.
Use Goodenough schemes, which are designed to capture shocks. They're very elegant. They have basically two components. They have a Riemann solver.
Yes.
And they use upwinded differencing, smart upwinding, depending on the direction of the propagation of elementary waves.
Yes.
But in doing so, they introduce dissipation. So they're great for capturing shocks. But then the question arises: what if you have a flow that has both shocks as well as turbulence?
Yes.
Then what these schemes tend to do is they will, of course, capture the shocks very nicely, but then the eddies will be dissipated.
Okay. All right.
So, of course, this problem has been recognized in the engineering community, and there have been several lines of investigation. I would say that till now, none has been completely satisfactory. Though I think there are trends, which I will talk a little bit later, which I think will help solve this issue.
Cool.
So I would say one of the best ideas is hybridizing, hybrid schemes. Where you somehow in regions where you have shocks, you bring in the shock capturing apparatus, but where you don't have shocks, you use a scheme like Padé.
Okay.
Now, I should mention, so let me just generally talk about the advantage of Padé schemes.
Okay.
So as I will show in figures later on, Padé schemes have a spectral-like resolution.
Yes.
So a spectral scheme differentiates exactly all the wave numbers that a mesh can support.
Yes. Okay. Mm-hmm.
And if you do de-aliasing, then, for example, using the 3/2 rule, then they also have zero aliasing error.
Cool.
And therefore, their rate of convergence is spectral,
Yes.
meaning that the rate of convergence is faster than any power law.
Good.
So Padé schemes have spectral-like treatment of derivatives. So they will, as they approach the capability of Padé scheme, they approach the capability of spectral schemes
Yes.
to give you an exact derivative.
Very cool. Very
Okay.
cool. Okay, I'm with you.
Okay. Now, I should mention that I haven't talked about aliasing error. That is a little technicality that I hope you will forgive me if I don't get into too much.
That's fine. That's fine. Just
Uh,
mentioning it is good. We're okay.
but there have been recent advances. So various techniques have been known, are known, particularly in the engineering community, to not completely eliminate aliasing error from finite difference schemes, but to reduce aliasing.
Minimize. Yes. Mm-hmm.
Okay, so now let me. So I think I've sort of given you a motivation for trying to pursue a Padé scheme. Namely, we want to reduce dissipation on vortical features.
Yes. Okay.
Okay, so if we then continue.
Okay. Let's go on down. Talk about the pencil code there a little bit. Okay.
Yes. Well, let me just mention the pencil code. So the pencil code doesn't use a good enough scheme.
Correct. Yep.
So it uses a central finite difference scheme, but then central schemes are prone to, well, you need some kind of dissipation. So either so, so there is a term called direct numerical simulation, which
Yes.
is where you resolve all the scales of the flow, but for
Yes. Mhm.
astrophysical flows, the Reynolds number is very high.
Yes.
We can never hope to resolve all the scales.
Right.
So you need some subgrid treatment.
Good. Okay.
And so one type of subgrid treatment is called implicit LES. And in fact, the good enough type schemes that I mentioned before, what they do is they rely on the dissipation of the scheme to
Yes.
provide a subgrid treatment.
Yes.
In engineering literature, because the physics is a little less complicated, you don't have magnetic fields, radiation, etc., then you can try to use an explicit subgrid scale model. For example, in the atmospheric community, there's this Smagorinsky model, which is also used in the engineering literature, and there are newer models, also explicit models. But generally, or not at all, in fact, in the astrophysical community, I have not seen a single paper that uses an explicit subgrid model. For example, Smagorinsky's model. They all typically rely on the numerical dissipation of the scheme. The pencil code uses upwinding.
Dissipated.
As far as I know.
Yes.
Okay, so then let's get into what this code does. Okay, so we solve the equations of motion with the Euler terms in cylindrical coordinates. And I should mention that in the future we should also have the capability to do spherical coordinates. For example, for disks, if you want to do a global domain with a bigger radius, then the disk grows in height, and so spherical coordinates are more appropriate.
Okay, cool. I'm with you.
Okay. So currently, we only have a point source of mass at the origin. In the future, of course, self-gravity would be a good thing to put in, a Poisson solver.
Indeed. Okay.
Now, I want to mention something about the Fargo scheme. So the So for protoplanetary disk flows, the time step restriction, if you don't do anything, comes from the very fast Keplerian advection.
Okay, yeah.
Because the Mach number of the turbulence itself is low. So the eddies move at speeds which are small compared to the speed of sound.
Yes.
So the limitation really comes from the propagation of sound waves. But the Keplerian flow, its velocity is several Mach numbers.
Okay.
So much higher than the speed of sound.
Okay.
So you'd like to reduce the time step restriction from this very fast Keplerian advection.
Yes. Okay.
So Massey in 2000 came up with a clever idea called Fargo. And so what he does, so his idea, which has now been implemented, for example, in the Fargo 3D code and many other codes, including Pluto, and I think Pencil as well, is
Pluto up here. There's a little guide there to Pluto.
So the Fargo idea is to do the following. So you basically you treat the Keplerian advection by an explicit shift. So
on shift. Okay.
So you shift your flow field by an amount, by a certain number of integer grid cells.
Okay.
The nearest integer to, normally the Keplerian advection will be a different shift in the azimuthal direction by a certain angle, which varies smoothly.
Okay. Okay.
But the idea of Masseau was to use the nearest integer.
Okay.
Because it's easier to shift by an integer amount than a real valued amount.
Indeed. Yes.
Okay. So what we recognized in around 2018, so myself and Alan Ray, that really underlying this scheme, so if you want to be rigorous about it, then really what is happening is a change of coordinates. And so when you have a change of coordinates, then you have to then chain rule terms come in when you apply that change of coordinates to the equations of motion.
Yes.
And therefore, you need to include these extra chain rule terms.
Good.
The other thing that we recognized was that what the integer shifting does is it introduces a jump in the shifting. In other words, if you look at the previous paper, there is a plot of the number of intervals of grid cells that you shift.
Okay.
And so that'll be constant for a certain range of radius, and then for another range of radius, it will jump to a different shift. And so that effectively introduces a delta. So as the grid is refined more and more and more, that jump introduces a delta function error in the scheme.
Okay. Okay. Good.
So we basically corrected both of those issues, and essentially our Fargo implementation introduces the chain rule terms, which are necessary for consistency.
Yes.
And it does a real valued shift. So the jump due to integer shifting goes away.
Goes away. Yep. Cool. Very good.
So of course this involves more work, more computation, and sometimes, for example, when you're converging a code to statistical stationarity, the code allows one to revert to the original Masseau scheme. So you can, while you're to steady state, you can go back to the integer shifting, and you can forget about these extra chain rule terms. And then when you're statistically stationary, you can say, okay, now I really want the accurate flow, and then you can turn on the more accurate treatment.
Cool. Okay.
Okay.
Very good.
Okay. So that's basically Fargo.
Cool.
Okay, so the next thing that I would like to talk about is shock capturing. Okay, so the Goodenough scheme is, of course, very elegant, very nice, and now we have this Padé scheme. So what do we do when we have shocks? So what we have done is, and this is not as elegant as the as the good enough scheme is a treatment that was developed by Cook and Cabot, which is basically a extension of the old Richtmyer and Meshkov from World War II shock
Yes.
capturing,
Yes.
which is a 1D treatment. So what do you do in 3D? So what Cook and Cabot sort of realized is that a 3D extension of the Richtmyer and Meshkov artificial dissipation is really a bulk viscosity.
Okay. Sure.
So a bulk viscosity is so normal viscosity is a viscosity that a viscous stress that's proportional to the strain rate.
Good.
But a fluid which has a bulk viscosity has an additional stress that comes in when there is dilatation, also when the flow is compressing or expanding.
Good. Okay.
And what that does is it introduces an additional pressure. And so equation 22, for example, so we have a numerical bulk viscosity, which is denoted beta sub delta, and that introduces an artificial pressure.
Due to compression or expansion. Yeah.
Okay. And so the effect of this is to smooth out shocks, but it's so this viscosity is sensitive, first of all, to the dilatation. It will only act where there is where there is compression and expansion.
Just like Richtmyer-Meshkov. Yep.
But then in addition to that, the coefficient itself, so the beta sub delta, so equation 23, that is also sensitive to just dilatation.
Yes.
So this viscosity will not act where you have eddies. It will act only where you have strong dilatations.
Good. Okay.
Perfect. Of course, we cannot have the mathematical proofs of good enough schemes, namely that they are TVD, total variation diminishing, or ENO, essentially non-oscillatory. So we don't have those mathematical proofs, but it's I would say for protoplanetary disks, we really don't have. Turbulence is subsonic.
Yes.
So we don't have very strong shocks. We could in the future, for example, if we have a planet moving at sub-Keplerian speed, moving relative to the Keplerian flow at a supersonic speed, then it's going to create shocks. And so then, there are situations where shocks might arise. And so for that purpose, we have this artificial pressure bulk viscosity treatment.
Okay, very good. I'm with you.
Okay. So now let's talk about Padé, the guts of Padé differentiation. I just wanted to mention historically, Copal doesn't really get the credit that he deserves. For example, I thought that maybe I should call the code Copal instead of Padé.
That would have been cool. Okay.
Because Padé, the mathematician, really did not come up with the scheme. It was Copal that came up with the scheme based on what's called Padé approximants.
Okay.
So let me just very briefly mention what Copal understood. It's a little I would say abstruse when you actually look at his book, which I
we're gonna see one. Oh, I'm gonna have you pull that up.
I have you.
I'm gonna have you do that later too. Okay, very good.
Okay. So it's a book on numerical analysis, but Copal was actually an astronomer, but who also got into numerical analysis. Czech born, but worked in England. So Copal's basic idea was the following. So you can so in numerical analysis. You have difference operators. You have a forward difference operator. You have a central difference operator. You have a averaging operator.
Yeah.
And it turns out that you can write one operator as a function of another operator.
Okay, sure.
An exact function. So for example, the difference operator, you can write that as an exact function of other operators. For example, the averaging operators. And then you can Taylor expand that function,
Okay.
that operator function.
Mm-hmm.
And if you do that, then you get regular, normal, finite difference schemes.
Right.
But Copal's idea was the following. He said, let me take this Taylor expansion and write a rational function. So a Padé approximant, and we know from the theory of Padé approximants that a rational polynomial representation of a function has a greater radius of convergence and approximates a regular function that varies very rapidly better than the Taylor expansion.
Uh-huh. Good.
And so in the present case, what it does is it gives you a scheme, a finite difference scheme that has better resolving power, which I will explain.
Yeah.
So,
Gotta give an order. Mm-hmm.
yes, actually, before we go on, let me show what the simplest Padé scheme looks like.
Okay.
Okay, and so this is called a standard Padé scheme, equation 27.
Yes.
So let me take a sip of coffee before I go on.
Have a couple sips. It's all good.
Okay, so let's look at this equation and focus on just the middle term of the left-hand side, just the middle term.
F prime.
So if we just focus on the middle term, it says that the derivative at j,
Yes.
now we go on to the right-hand side, is a difference of the function f, a central difference of the function f. So if you just look at that, you have a central difference scheme.
Yes.
Your standard second order central difference scheme.
Yes.
But
Try
now
it.
going back to the left-hand side, we see that it's a linear combination of the derivative at other neighboring points.
Mm-hmm. Yep.
And in fact, this left-hand side arises from a rational polynomial. It's sort of the denominator of the I don't expect you to see that right away in your head, but this left-hand side actually arises from the denominator of Copal's rational polynomial, and what you get is a linear combination of the derivative at 3 points.
Yes.
Equals your normal central difference.
Cool. Very cool.
Okay, so let's say that you wanted to take a derivative along, say, the x direction, then what do you need to do? Well, so if you write this equation in matrix form, it actually is a tridiagonal matrix.
Yay.
Because on the left-hand side, you have the derivative at 3 points.
Uh-huh.
So if you write this, for example, at 2, the derivative at 2 involves the derivative at 1 and 3.
Yes.
And then if you go to the derivative at 3, then that involves the derivative at 2, 3, and 4.
Mm-hmm. Yep.
And so then all the derivatives are coupled. So the derivative at a given point does not only see the value of the function at neighboring points, it sees all the values.
Yes. Uh-huh. Uh-huh. Cool.
And in fact, we know that really the derivative at a given point, if you think about spectral representation in terms of sines and cosines, the derivative at a given point really should know about, if you want greater accuracy, should know about the value of the function at all the points.
Sure. More than its nearest neighbors. Yes.
Yes, more than its nearest neighbors. And so that's what the Padé scheme does at the expense of having to solve a tridiagonal matrix.
Which is not so bad.
Which is not so bad, but I should mention that for parallel machines, then
Right.
it requires you to have. So if you're taking a derivative in the x direction, it requires all the values in x to be in memory.
Right.
So then, if you're differentiating in x, all the x's have to be in memory. Now, if you're differentiating in y, then you need all the y's to be in memory.
Correct. Yes. You got to know the full thing.
So the traditional way to do that is to do a transpose. So the normal data structure is what we call a pencil data structure, which are basically long bricks.
Mm-hmm.
So then every processor has a long brick with all the x's.
Yes.
Now, when you want to do a derivative in y, then you do a transpose so that the processor also has all the data. Each processor has all the data in y, but these transposes involve all-to-all communication, and so they're communication intensive. And so the current code uses transposes. And
Okay.
I will later on come to the cost that it involves. But I should mention that actually, since many years now, arising from Stanford Golub, for example,
Yes.
um, have developed schemes that can now allow parallel tridiagonal inversion.
Very cool.
And so I'm actually working with a group in Korea
Cool.
that have developed a package to do this. And so
Nice.
I want to implement that in the code. And I should also mention a development at Stanford in the aeronautics department where they're developing something called Padé libs. So this is a set of packages
Yeah.
that really will allow easier
Mhm.
easier use of Padé schemes.
Nice. Good,
Uh,
good.
and I'll mention that a little later on. It's the group of Sanjeev Lele, the main student that's developing this. His name is Hang Song, and I will give a shout out to him perhaps if I have time at the end.
I think you just did, but we can do another one.
Yeah. Okay, so it's
Okay.
called Padé libs at Stanford. Okay,
I'm
so now,
with you. Mhm.
so now, how do we assess the resolving power of a Padé scheme?
Yeah, how good is that? Mhm.
Right? How good is it? So the method that we use is something called a modified wave number analysis.
Okay.
So what we do is, so if we look at equation 29, we plug in a discrete Fourier mode. So
Mhm. Right.
so we plug in f sub j equals exponential of I k
Mhm.
x sub j.
Right.
Now, if the differentiation were exact, then f prime at j would be I k e to the I k x j. But
Uh-huh.
since differentiation is not exact, we end up with some effective wave number.
Okay. Yes. Uh-huh.
K effective. So what we then plot, and if we can go up to the figure.
Yeah, let's go to figure one.
Okay. So then figure one plots the K effective versus the K, okay, normalized by the grid spacing H.
Okay, I'm with you.
Okay, so if we had exact differentiation, then K effective would equal K,
Yes.
and we would get the solid line.
Mm-hmm.
And so that would be spectrally accurate. So that's what a spectral method would give you.
Gives, yes, agreed.
So now, if you had a sixth order Padé scheme, then you would get the purple line.
Yes.
If we use the fourth order Padé scheme, which is the one that I have implemented in the code, the only one currently implemented in the code, and which I displayed in equation 27, then you
Yes.
get the green line.
Okay.
Okay. Now, by contrast, if you look at a central fourth order scheme, then you get the dashed. So that is lower than the Padé fourth.
Yes.
And if you look at central second, then you get the dash line.
Yes.
Now, I just want to mention, so there are several codes that actually many computations in the literature actually use second order thing.
Oh yeah.
Which would give you the dash line, and on top of that, they have dissipation. So then you can imagine how badly, how many grid points you really need to resolve your wave number range, right?
Right. Correct. Mm-hmm. That's cost. Yep.
Yes. And from experience, I would like to say that whenever I have seen what even this fourth order Padé scheme gives, you really see much more structure when you look at the result of a computation compared to a central scheme.
Good. Yes. Correct. Correct.
Okay. Now let me just mention something about this figure B, since it's in front of us.
Transfer function. Okay.
Okay. So what's this Padé filtering all about? Okay, so supposing we were doing a direct numerical simulation. So now everything is
DNS. Mm-hmm.
DNS. Everything is well resolved.
Yep.
So if you look at Lele's paper, then he mentions from 1992 that Padé schemes produce small wiggles, and you need to filter them out.
Okay.
And so in his paper, Lele introduced these filters which have kind of a very similar form to equation 27, but they're actually filters rather than differentiators. And so we use the Padé filter to, every few time steps we apply a little bit of filtering to get rid of these very small wiggles,
Right.
which possibly arise from aliasing error when you have nonlinear terms. So
Yeah.
so far, I've not mentioned anything about nonlinearity. So typically, so
We'll get there.
so when you have a spectral scheme, you typically use the 3/2 rule to eliminate aliasing error.
Yeah.
But here, so how do we deal with aliasing error here? And so the Padé code actually currently doesn't have any method of doing de-aliasing.
Okay.
But in the engineering literature, and by the way, my tech plot came up again, so I'm gonna see if I can close it.
Awesome.
Sorry about that.
It's all good. We don't see any of it, so it's all good.
Okay, let me just actually force quit it. So
Wait.
just, I'll come again. Okay, so going back to Padé filtering. So so I believe that from the work of the Stanford group, Hang Song, based on previous work in the engineering literature, that you can reduce aliasing error. And the way the way you do that is, so there are two approaches. One is writing the nonlinear terms in the equations of motion as an average of conservative
Okay.
and non-conservative. So you
Okay.
take the average of the two, and you can show
Okay.
that has lower aliasing error. Another is to use staggered
Oh.
staggered representation of different variables. So some variables
Yes.
are cell-centered and other variables are grid-centered. And of course, that involves some interpolations that you have to do, but that reduces that gives you lower aliasing error. And in fact, the group at Stanford has shown that with that, you don't need any more filtering.
Very cool. Very
But
nice.
But this is if you're doing DNS, okay?
Yes,
So
understood.
DNS, no more, okay, filtering. Okay, so I mentioned earlier the need for subgrid scale modeling because we can't resolve all the scales. So, of course, it would be nice in the future if the astrophysical community started to think more about explicit subgrid scale modeling.
Okay.
Now, of course, given the complexity of the physics, radiative transport, magnetic fields,
Yeah.
it's not going to be an easy task. But I do believe that the astrophysical community should start thinking in that direction because till now we use the dissipation of the numerical scheme.
We do, generally, yes.
Generally, and there is no reason to believe that the effect of the subgrid scales, the nonlinear effect of the subgrid scales on the resolved scales, should have anything to do with numerical dissipation.
Okay.
Of course, from a intuitive point of view, it's okay. We know that generally the role of subgrids, the first order role, the first order role of subgrid scale turbulence is to provide dissipation.
Yes.
But we also know from experience from magnetic field physics, MHD physics, that you can get an inverse cascade when you have helicity. So the role of subgrid scale turbulence is not only to dissipate; it has other roles as well. Also, if you look at the eddy viscosity provided by subgrid scale turbulence in wave number space, it's not flat.
Right.
So the dissipation is some function of the wave number
scale, right?
And so you want to represent that precisely, and the numerical dissipation introduces a particular kind of dissipation that does not exactly mimic the dissipation provided by subgrid scales.
Okay. Yes.
So I think we should start thinking about these issues. But okay, in the future,
that was good.
and I don't tackle any of that. So I use the implicit idea, namely, but the dissipation that I add, because the Padé scheme doesn't have any dissipation, I have to add some dissipation for some modeling.
Yes.
And for that, I use a Padé filter, but a stronger version of the Padé filter.
Okay.
And actually, later on, I will show a set of simulations where we vary the Padé filter, and we'll see what that does to the to how we're able to resolve
the effects on. Yep. Very cool. Oh, I'll be patient till we get there. Okay.
Okay. Okay. So let's just continue on.
Okay. There's our filtering, which you kind of covered. Boundary conditions.
Yes. So it's very so I want to talk a little bit about boundary schemes and global conservation.
Yes. Okay.
Okay. So the important point that I want to make is that so most codes, so the pencil code is a finite difference scheme, finite difference. But most other codes, the ones that use good enough schemes, are actually they use a flux differencing.
Yes.
So they reconstruct a flux and then they take a difference. And so what that ensures for you is that because the derivative or the rate of change at a given point or in a given cell is a difference, then when you add up all the differences, they collapse. And so you get a difference of only boundary values.
Yes.
So,
okay.
so you end up with a conservation property. But
Cool.
in the present case, the scheme is a finite difference scheme. And so you want the same conservation property.
That'd be nice.
And so what do you do? Well, it turns out that you need to, you can develop boundary schemes that then give you an overall scheme that has a conservation law property. In other words, there is some kind of collapsing of derivatives so that you end up with Leibniz's rule, namely that if you integrate a derivative, you end up with a difference of boundary fluxes.
Okay. Yep.
And so that's a little bit technical, but it's described in Lele's paper how to do it, and the appendix of this paper basically describes how to develop, how you can ensure that your boundary schemes give you an overall scheme that has this Leibniz rule property.
Right. There's 2 appendices in this article, people, so check it out.
Okay. So let's then move on.
Okay. Leibniz rule. Yes. Good. Good. Okay.
Okay.
Leela 92 and partitioning maybe.
Okay, so I mentioned that the code uses transposes, and so the data structure uses pencils, and so this is a brief description of I put this in so when someone first looks at the code, just very basic information that a person wants to know is what array stores the variables.
Right.
Well, you know that this variable is called Q. And then it shows what the indices, represent. The very first thing that you want to know when you look at a code. That's all I wanted to transmit here.
Very cool. Good.
Okay. So I wanted to mention that it's unclear. So we have a fourth order scheme. And so with nonlinear, and of course the convergence arises from a Taylor series expansion, not there's no nonlinearity there, and so one might be suspicious that is the overall scheme fourth convergent, and in particular is it convergent with multi dimensions.
Okay.
And in fact, the referee had that objection or had that doubt.
Concern.
had that concern, and so this test case was actually done to satisfy that.
Good. Little
Yeah,
shot
concern.
down right
Uh,
there.
so-
Yay.
and so basically, this is a test case of linear advection. So
Okay.
it's not, but it's in two directions. So it's advection in the z direction and advection in the phi direction, because the referee actually thought that we were doing operator splitting,
No. That's bad.
which
Yeah.
which is not what we're doing.
Right. Correct.
Um,
Yep.
and so basically, then this plot shows that for this particular test case, in fact, we do get fourth order.
Okay, let's take a look at that figure 2. Let's take a look at figure 2. Let's see what we got. Figure 2, convergence test. Okay, RMS error. Its function, grid number. Okay.
Okay, fourth order convergence.
Good.
So another test case, which is popular, for example, when you look at the papers on Athena,
For example.
for example, so they use this test case of a Kelvin-Helmholtz instability.
Okay, let's take a look at Kelvin-Helmholtz. KH, yep.
By the way, I just wanted to. So okay, is that the one that comes next? I don't want to
No,
skip.
well, then the next one was actually a shock, Euler shock.
Okay, so let's actually do the shock.
Okay.
So this is a shock tube case, and I actually want to show that unlike Goodenough schemes, there are some wiggles that you see, and so let's look at.
Take a look at figure 3. Figure 3. Here we go, and I'm going to zoom out a little bit to get them all. There we go. Okay.
For example, if you look at figure 3C, so I've zoomed in, and you see that there is some buzzing there. So obviously not as good as Goodenough schemes, but then Goodenough schemes are going to be more dissipative, right? Overall, let's look at figure D. So this was a test case that was introduced by Shu and Osher.
Yes. Shu Osher test case. Yes.
Okay, so what the initial condition here consists of, so you have a shock, and to the right of the shock, so if you look at the plot after x equals 2, for example, so you have some oscillations in the density.
Yes.
And then a shock goes through these density fluctuations, and they get amplified as they go through the shock. So this is a simple 1D test case that allows you to not only assess the ability to capture a shock, but then also assess the ability to resolve any wiggle, any smooth oscillations that you might have.
Right. Yep.
And so here, this figure,
Cool.
compares what the code does with the bulk viscosity shock capturing scheme against a Weno fifth order scheme using 1600.
Yeah. Cool. So that's pretty good. Chi by eye, very good.
Okay. So now let's look at the Kelvin-Helmholtz test case.
Okay. That one should show some pretty good. Yeah, Daedalus and Padé. Sure.
Okay. So the plot on the left shows what you get with the Padé code using 1024 squared points. The plot on the right, this was data given to me by Lequanet.
Yes.
So the Daedalus code is a spectral code,
Yes.
and this is what they get using 4096 squared points. And you see that the agreement is quite good. Now, I should mention, of course, really, maybe a fairer comparison would be doing a Daedalus code with 1024 and the Padé code with 1024.
Sure.
But this is the only data that
we got. So yeah, it's pretty good.
Okay.
Pretty good. A few little differences in some flow structures, but overall, pretty good. Okay. Cool. I'm with you.
Okay. Let's move on then.
Okay. Thank you, Daniel. Figure 4, table 1, torques, or table 1 if you want to cover that, or you want to go to the Taylor-Couette flow.
Yeah. So table 1 is actually Taylor.
Oh, it is. Okay.
So let me say, just just something about doing Taylor-Couette flow. So obviously it's when you have a code in cylindrical coordinates, Taylor-Couette flow is a very good test case to have.
Yeah.
And I should also mention that the code has viscous terms. So why did I code viscous terms even though the viscosity is very high in protoplanetary disks? Well, so I did want and I have implemented explicit subgrid scale models.
Okay.
And so, for example, the Smagorinsky model, the a model de Touv-Raymond. So I have implemented them, but I've not really tested them. So anyway, so this is viscous Taylor-Couette flow with laminar viscosity, and so basically, if we can see particularly a plot of the torque, which is I believe on the next.
Go to figure 4. Let's take a look at that. Figure 4, Couette flow. There you go.
Yeah.
Okay.
Okay, so this is for for a test case done by so let me see. So the left hand side is for a Reynolds number of 500.
Okay. Here we go. Okay.
The right hand side, I forgot whether that's a different Reynolds number or no. Actually, no. So this is both Dong's test case.
Yeah, it should be the same. Yeah.
Yes. It's the same.
Yeah, must be.
So the the black line shows what we obtained for the torque coefficient as a function of time, and the red line shows what Dong obtained. Of course, they can't be the same because different random numbers, etc. So one should only look at the sort of statistical, whether on average they're the same.
Right.
The torques agree.
Pretty good.
Quite
pretty good.
And the number of grid points was in the caption.
Yeah.
48 by 96 squared.
There you go. Cool. Okay. Fairly light, but good. Nice. All right.
So I would actually recommend.
So far.
I would actually recommend. If your code has viscous terms, then I would recommend Taylor-Couette as a
yes. Check that. Very cool.
Case.
Doing good. Passing all tests so far. Within reason.
Okay, so let's just move on from Taylor-Couette.
Okay, so what we got. Then you want to cover some of the vertical shear instability?
Yes.
Strength of the filter?
Yes. Yeah, let's do that.
Let's cover that. Whoops. Let's cover that. Okay.
Okay, so this Padé filter that we're using for implicit subgrid scale modeling. So it has a parameter, epsilon filter. So how do we pick that? So if we pick it to be too small, we're going to get wiggles.
Yes.
And if we pick it to be too large, then we aren't really using the capability of the Padé scheme to resolve small scales, right?
Right. You're doing more work than you got to.
So we have to do some experimentation, and really these test cases were some experimentation to guide me towards 3D calculations, which I then subsequently did.
Okay, very good.
So then let's look at what the flow looks like if we vary this epsilon filter.
Okay. Let's go down to the next one.
Yes.
Okay, so this is a big one. So I'm going to zoom out to get it all, and then we'll zoom in as need be. So I understand that's a little small right now, but we'll go okay.
Okay. So this is vertical shear instability, axisymmetric calculation in this case because it's just a test case. Okay, so this is a instability mechanism that was sort of discovered, or I would say rediscovered a few years ago, which arises in protoplanetary disks.
Not for one.
Because there is because protoplanetary disks have a temperature gradient in the radial direction.
Yes.
Then from the quote unquote thermal wind equation, baroclinic generation,
Yes.
you get a vertical shear. So the Keplerian shear not only has a gradient in the radial direction, the Keplerian gradient, but it also has a small gradient in the vertical direction.
Yes. Okay. Okay.
Okay.
Uh-huh.
And
I'm
then
with you.
okay, and then the other ingredient that you need, so not only vertical shear, but the other ingredient that you need is a suppression of buoyancy. So normally buoyancy, for example, in our atmosphere, you get these Brunt-Weissel oscillations in a stably stratified atmosphere.
Yes.
And in fact, the general temperature profile in a protoplanetary disk is in fact stably stratified
Yes.
in the presence of buoyancy. But if you have rapid cooling,
Yes.
as you know, in the atmosphere, the buoyancy effect arises because a parcel, when it moves downward, it's adiabatically compressed,
Yeah.
and then and then it's buoyant upward, and then it expands and is buoyant downward, and so you get these Brunt-Weissel oscillations.
Yep.
But if in a protoplanetary disk, the temperature of this parcel adjusts to the background temperature, then you lose the buoyancy.
Yeah, that's going to suppress it. Mm-hmm.
Okay, so that suppresses the buoyancy. And what that does in the protoplanetary disks, in the presence of this vertical shear, is to give you these jets vertically. So you have counterflow jets, upward jet, downward, next to a downward jet.
Okay. Plumes and risers, yes.
And the vorticity field associated with these jets, of course, is these shear layers.
Mm-hmm.
And these shear layers undergo Kelvin-Helmholtz instability.
Indeed, yes.
So this shows an axisymmetric simulation of this vertical shear instability, and I vary the strength of the filter.
0.01, 0.04, 0.125 as we
go. So let's actually begin at the bottom, which is the strongest value of the filter.
All right, let's zoom in on the bottom a little bit.
Okay, so here the filter is 0.125.
Mm-hmm. And
you see the shear layers, and you see the Kelvin-Helmholtz instability on the shear layers.
Yeah. Uh-huh. Uh-huh.
Now let's go to the middle figure.
Okay.
And by the way, let's just look at the right-hand side. So the right-hand side is a zoom showing the grid also at a given location. And so you don't see any 2 delta wiggles, right? Everything is fairly smooth, right?
Fairly smooth. What is this? This is a 512 square. Okay. Mm-hmm.
Okay. And so now let's look at the middle figure.
Okay. So now we're going to back off on the filter.
Yeah. So we're going to do it now to 0.04. Okay. So you see that you have many more small
fine structure. Yes.
You have finer scale features. And if you look at the right-hand side plot, you see that the shear layers are thinner, the eddies are smaller, and also more intense. So in fact, now you see there are these white regions. So basically, the white regions are those which are off the scale. So they are higher than the vorticity value that you see. They're higher than the 135. So the vortices are even more intense. But now you say, oh, did I create any wiggles by doing this? And I really, it still looks pretty smooth.
Still looks pretty good. Mm-hmm. Great.
Okay, now let's go to the top one, which is the lowest value of the filter.
Back it off even more, and more structure.
Okay, so now this is 0.01, and you see more structure.
Mm-hmm.
But if you look on the right-hand side, okay, you probably don't see my cursor, right?
No.
Okay.
Tell me where to point. Give me some RZ locations you want to go.
Yes. So go a little bit higher to the left.
Higher and to
higher. Go to the blue eddy. Yes. Now go to the shear layer of that eddy.
Okay.
If you look very carefully, there is some wiggles in the shear layer of that eddy.
Yeah, there is a little bit. And you can kind of get a sense there as well. Yeah. Okay. So maybe this is a little too little of a filtering.
Yes. Okay.
Okay.
Actually, so in my 3D simulations, I was a little overly conservative, and so I chose the I chose the bottom value, 0.125.
Okay, a lot of filtering. So less
Yes.
structure.
Yes, structure. But then I also experimented in that paper, which hopefully should come out soon, where I reduced the filter.
Okay, cool. Well, we'll look forward to that one.
Get more structure.
Very nice. Very good. Good test. Good test.
Okay, so then this is on how to choose the. Okay, now this figure was done because the referee.
I knew that was coming.
So the referee wanted to see that with Fargo and without Fargo, we don't lose any accuracy.
Yeah.
Okay, so now Fargo allows for a bigger time step, and so without Fargo, you have to respect the CFL condition coming from the Keplerian advection, so it's a small time step.
Yes.
But now with Fargo, it's a bigger time step.
Yes.
So you're going to get bigger time stepping error, right?
Sure.
And so you want to make sure that that bigger time stepping error is reasonable, and so figure 8 on the left shows with Fargo, with a bigger time step, and on the right you have without Fargo a small time step. But both run for a. So let me see. It was so the run actually was started at 300 orbits, 300.27 orbits, and actually run for half an orbit.
Okay.
And I should mention, of course, because the flow is chaotic, if I ran it for 100 more orbits, they would look totally different, right? Because you get sensitive depending on initial conditions.
Yeah.
But I think half an orbit, it's still good enough.
So it's a way to test it.
Yeah. So I mean, still, there's a lot of advection that has happened in half an orbit, and the agreement is good. Right?
Okay. Yeah, in general, pretty good. A little stronger and a little more intense, I guess I would say, in Delta WZ, but yeah, broadly it's there. Cool.
Now, let me just mention a little bit about the physics here. So this is actually a 3D vertical shear instability calculation. Obviously, it's 3D. It's non-axisymmetric. And so physics-wise, I want to point out, you see these layers of vertical vorticity. So what a layer of vorticity does is it causes a jump in the azimuthal. So this is omega z, right? So this is pointing out of the page, that vorticity. So this jump in vorticity would result in this concentration of vorticity would result in a jump in azimuthal velocity.
Okay, sure. All right.
So this means that the Keplerian angular momentum has small jumps.
Ooh.
And in fact, this was pointed out, focused on in a paper by Mellon Fuchsman et al.
Okay.
Recently, and I've investigated it further. It actually so in the 3D case, there is a slight redistribution of angular momentum in the disk.
Okay.
And it turns out that in the axisymmetric case, it's much stronger. So you get a staircase of angular momentum, which I believe is an artifact of the axisymmetric calculation. So actually for the future paper, is that when you do axisymmetric vertical shear instability, please be careful.
Good morning. Yes.
Okay.
Yes.
Okay. So let's then move on.
Okay. So we covered the BSI, Fargo, non-Fargo.
Okay.
Oh, scaling test. That's always a good thing to talk about.
Okay.
Scaling test for the 3D BSI.
Yes. So actually, let's go to the figure 9A, for example.
Okay, let's go to 9A. I'm going to zoom in here a little bit.
Okay, so figure 9A is for a weak scaling test. So what a weak scaling test is that you keep the problem size per CPU to be fixed.
Yes.
So then as you vary the x-axis, the number of cores, the problem size is also getting bigger and bigger.
Okay. Weak scaling.
And what is plotted on the y-axis is something called is an efficiency. And I want to thank the referee here for educating me about weak and strong scaling tests. Thank you so much.
Okay.
And also for this quantity called the efficiency. So the efficiency is basically essentially how many grid points you're able to advance per work.
Yes.
Per wall clock time. But a wall clock time times the number of CPUs. Yeah. Can I please refresh myself on the definition of
sure, let's find out. Let's find out.
Let's look at the equation for Ada.
And Ada, here we go.
Okay, so the efficiency is the number of grid points that you're evolving. And let's actually forget the time step factor for the moment. Let's assume that the actual time step is the same as the Fargo time step. So then in the numerator we just have the number of grid points normalized by 2 to the 7.
Normalized by something.
Okay, and then in the denominator we have the resources we're expending to do the work.
Correct.
And so the resources is the wall clock time times the number of cores. Right. That's how much the taxpayer is paying me,
or someone is,
or how much the taxpayer is paying for this computer time. Okay, so that's what's being plotted on the y-axis. So then if we go back to
let's go back. Okay, now we got what data is. Okay, I'm with you. And let's go back to here.
Okay. So the efficiency that we get, so actual, without any. So this is the the bottom line. So we see that there is a decrease in efficiency as we increase the number of cores.
Yeah.
And this is because of the transposes that I mentioned, the all-to-all communications for parallelism.
Right, they don't parallelize well.
Yes. The transposes don't parallelize well. And so to see that, then if we subtract out the time of the transposes, then we get the dash line with the square symbols. And you see that after about 10 cores, then the efficiency is flat. So we get we get good scaling.
Correct. In the weak scaling case, yes.
In the weak scaling case. And so this suggests that we really need to put in the effort of doing these tridiagonal inversions using parallel Padé.
Yes.
So that's something I'm working on with the group in Korea.
Yeah, and, that's a great plot.
And also the group at Stanford, Hang Song,
using their libs.
Yes, right. using Padé libs.
Yes. That's a good plot. Good. Okay.
Now you might, I don't know if I should say anything about what's happening for a small number of cores.
Sure. Suppose you had just one core. Suppose it was serial.
Well. So why does the efficiency drop so rapidly for a small number of cores? So actually, both the referee as well as my colleague Alan Ray, who's a computer science person, helped me interpret that. And I'm really not a very good computer science person, so I've actually already forgotten what the reason for this is. But there is some computer science reason for this. But we don't really care because we aren't going to be running for a small number of cores.
I don't think anybody will be running serial. So yes.
Okay. And then the plot on the right.
Strong scale.
So B is a strong scaling test where you keep the total problem size fixed and you vary the number of cores.
Yes.
Okay. And so here, then you see that there is a drop in efficiency, but it's again, I'm not okay. Since I'm not a computer science person, I'm more a physics person. It evades me right now why the drop in efficiency is less percentage-wise than it was for the
weak scaling.
For the weak scaling test. Right. But again, what this plot shows is that if we reduce the cost of the transposes, then in fact the efficiency, I mean, it slightly increases in the strong scaling.
Very good.
And then the plot, the figure C,
with and without
shows the efficiency gain that you get from Fargo. So I mentioned that Fargo has these two additional things you have to do. Namely, you have the chain rule terms.
Yes.
That you have to evaluate for every derivative. And then you have to do the shifting using FFT.
Yes.
And so, but you can use a larger time step.
Right. Right.
And so this plots the efficiency, taking into account the increased time step that you're able to use.
Okay, very
so
cool.
If you go back to the definition of that eta, you will see that there's a ratio of the actual time step to the to the time step so the time step you would have with Fargo and without Fargo, that ratio enters into that.
Right here, coefficient 7, and you get that there.
Okay, so then this shows that you get an increase of efficiency when you do Fargo, even with the additional cost that you pay for
doing all the extra work.
For the chain rule terms.
Very cool. Good. That was it. Okay, that's figure 9. Let's see if I can find that somewhere. Okay, good. I'm with you. All righty.
Okay, so this basically ends the paper. The appendix describes just the viscous terms, which actually, if you want to implement a Smagorinsky model or a Raymond's model, which we have done but not tested, then you would have viscous like terms to
yes, absolutely. Absolutely.
And then the second appendix deals with how you get discrete conservation, choosing boundary schemes so you get discrete conservation.
Yes, very cool. And I think it's at the end here. Maybe it's not. Let's find it. Let's do a find. And just to put out a nice advertisement, there we go. You can go grab it, people. It's on GitHub. Go grab a copy if you want to experiment with this particular version of the Padé and so on. So very cool.
Okay, so now let me just mention something about, I would like to obviously see more general codes. So this Padé code currently doesn't have self-gravity, doesn't have radiative transport, cannot do very strong shocks. For example, I actually tried to use the code for the infall problem. So I actually have a paper on infall, and I'm working on infall with the Pluto code, not with the Padé code.
Okay.
Pluto's
good.
Okay, so what are the prospects, and how can we get Padé scheme, the Padé scheme, and develop codes that are more general?
Okay.
So one thing which I think will help the community do this, evolve, is so here I want to give a shout out to and a plug to a group at Stanford in the engineering community. So Professor Lele, who first developed Padé schemes.
Yes.
In fact, he realized at some point that his group was getting behind the curve in using GPUs, still having the transposes, still having the filtering to deal with. And so luckily he got, G.K. Bassler said that graduate students are the princes of our field.
Yeah.
And they truly are. So he has a very clever, resourceful student who just graduated, Hang Song. So him and other graduate students developed something called Padé Libs.
Nice.
Where they have developed subroutines, tools, which allow one to use Padé schemes using the parallel Padé inversion, so without transposes.
Yeah, very good.
using staggered meshes.
Hmm.
So you eliminate the need for filtering.
Good,
And,
good.
and, and so my vision, and then perhaps even, I don't know, I believe they also have Poisson solvers that they have developed. So
There's your gravity.
if we wanted to do self-gravity,
Hmm.
we could possibly do it. Um,
Cool.
and then, recently there has been a success um, uh, in using in having radiative transport schemes with multiple streams,
Okay.
well,
Hmm.
PDEs, using flux limited diffusion.
Okay.
So those could possibly be implemented using Padé schemes.
Uh-huh. Uh-huh.
I believe that Hong Song's group has also hybridized Padé with shock capturing schemes.
Okay. Hmm.
Like,
Oh, yeah. So from Goodenough to Padné,
yes,
that transition.
well, yeah, right. So you do the Eno only where the shocks are present, and everywhere else you do Padé, so you get the higher
Yes.
resolution.
Yes. Uh-huh.
So I hope
Excellent.
that uh, that the astrophysics community can benefit from this development. Um, I do generally believe that um, uh, the astrophysics community needs to pay more attention to fine scale turbulence.
Okay. Right.
Uh, so, of course, in the protoplanetary disk field, uh, we we know that there is uh, for planetesimal formation, there is a tension between the role that the presence of gas and turbulence plays in perhaps promoting particle concentration that
Yeah.
may aid planetesimal formation, but on the other hand, turbulence causes dispersion, diffusion of particles, which
Win.
hurts concentration. And to know who wins in the end, or what the micromechanisms might be
Yep.
that help or hurt planetesimal formation, you really need to know what the fine scale structure of turbulence is.
Yes, you do. Hmm.
And I don't know much about other fields, but perhaps so for example, what is the fine scale structure of MHD turbulence? What is the fine scale structure of MHD turbulence with Hall diffusion and ambipolar diffusion?
And B field. Hmm. Yep.
Right? And how does that MHD turbulence interact with other hydrodynamic modes of turbulence? So I think for all these, we really need to resolve the fine scale structure of the turbulence.
Cool. Very good. Well, I
And
think getting this code out on GitHub and inviting the community to have at it and go at it is a great development.
I hope so.
Very cool. Very nice. Well, I really look forward to seeing this Padé based tool growth, and it'll be really exciting to see it go over the next couple of years as you start adding on new capabilities and other things. So very cool.
Okay, thank you.
Karim, thank you so much for walking us through your very lovely article.
You're very, very welcome. It was my pleasure.
And
And
now,
and I should say that I'm available by email. So please, if you have any questions, contact me. Um, if you have any test cases you might want to run, I can help you get started with the code. If you want to be introduced to the group at Stanford and start using Padé libs, experimenting with Padé libs,
put
you
an
can
offer.
do that. And I would like to have my uh, eyes, looking at the developments that I might not be doing personally, but whatever you are doing, keep me informed.
Very cool. Very cool. Who can resist that personalized offer? That is awesome. Very good. Very good. And that will do, everyone. And I hope this made your Padé Astronomy Day just a little bit better. And we will see you on the next one. Bye bye.
Bye bye.